Hello, Professor Sargent here with you again. The first question here is a question that I found on the Texas A&M Galveston website. However, the page seems to have disappeared, and I've extended the question to the second one. You may notice that the input into the logarithm and the base have been reversed on the thumbnail. Does that make a difference? If I can remember, I'll discuss that at the end of the video. As for the first part, I want to show a solution that I came up with, but also discuss how at the Texas A&M Galveston website, I saw them solving it, because we're going to apply something similar to the second question. If the log of 3 in base 2 is rational, there are two integers, m and n, with n not equal to 0, and furthermore, we may need to talk about the fact that m and n, reducing that would be in simplest terms, i.e. that there are no common factors. Such that the log of 3 in base 2 is equal to m divided by n. If that is the case, then by the definition of logarithms, that base of 2 raised to the power of m over n would equal 3. If we raise both sides to the nth power, we will still have equality, and on this side, the n's will cancel. So we have 2 to the nth equals 3 to the nth. We do a little erasing here. Keep in mind, though, that m and n are integers, so these are integer powers that we're talking about. N is not equal to 0, and there are no common factors. My solution to this was to say that the left-hand side will be even. Whatever m is, it is an integer, in fact, a positive integer. And so however many powers of 2 we have, we're going to have something that is even. And similarly, whenever n is some positive integer, then an odd times an odd is odd, times another odd is odd, so that whole right-hand side is odd. These cannot be equal. And so no, the log of 3 in base 2 is not rational. By the way, regarding the thumbnail, the log of 3 in base 2 equals the natural log of 3 over the natural log of 2, and that would be the inverse of natural log of 2 over natural log of 3, which is the log of 2 in base 3, which is what was referred to in the thumbnail. And so, since that's not rational, its inverse would not be rational either. So to address the second question, I want to talk about first how the first question was handled by the website at Texas A&M Galveston. And we had 2 to the m equals 3 to the n if the log of 3 base 2 was equal to m over n. And what they talked about was applying something known as Euclid's lemma. which states that if P is prime, P divides A times B, then either P divides A or P divides B. This gets abbreviated using this symbol. Be careful, that is not a forward slash. This, for example, is not saying P divided by A. It says P divides A. It is a divisor of A or a factor of A. So 2 will divide 2 to the nth power, since 2 to the m equals 3 to the n. Then 2 will divide 3 to the n. And although only 2 factors were referred to here, we can extend that to finitely many. So this would give us that 2 divides 3. Or vice versa, we could have argued that 3 divides 2. Neither one of those is true. So again, using Euclid's lemma or the extended version. So for the second part, the extension of the question, let's assume that this is rational. Then as in the first part, we would have integers. Well, we would have these 2 integers again, m and n is not 0. No common factors if we need to include that part. It implied the definition of logarithms. Base of A, power of m over n, that equals b. Raise both sides to the nth power, and on the left side have the n's cancel. Suppose that P is a divisor of A, where P is prime. Then P is also going to divide A to the nth power. But A to the nth is equal to B to the nth. But if P divides B to the n, then by the extended Euclid's lemma, P divides B. And without loss of generality, we will also have that if we have a prime P where P divides B, then P will also divide A. So in other words, when we do the prime factorizations of both A and B, we're not going to see any different prime factors in the two. What may differ is the exponents. Rate A equal to p sub 1, the first prime, raised to an exponent of e sub 1 times a bunch of primes raised to powers. And the last one will be p sub s raised to the power of e sub s. So these are primes. And the exponents will be counting numbers. Similarly, we're going to write a prime factorization of b. But we have all the same primes. What may differ is the exponents. Also, s is a counting number. Because we have a to the m equals b to the n. We're going to raise this to the nth power and this to the nth power. And for lack of a better word, distribute the exponents and multiply. Since these are equal, and obviously neither side is going to be 0, I'm going to divide both sides by this. And since we're not dividing 0 by 0, then something divided by itself is 1. Grouping by each case where we have the primes the same, and applying the subtraction rule for the exponents when we have a quotient with the same base. We'll have this. And my claim is all of these exponents are going to be zeros. That's not the case for all of these exponents for all of the primes that we have involved, then Some are going to be greater than zero. You might have some that are exactly equal to zero, and then some are going to be less than zero. So let's say that we have arranged these such that there is a counting number between 1 and s, call it t, where we have the following. All of these exponents are greater than or equal to zero. And then once you go past t, on up to s, that those will be less than zero. If we switch the order of subtraction, we'll be dealing with positives, by the way. And notice that since the exponents were counting numbers and m and n were integers, that we have to be dealing with integers here. Again, switching the order of subtraction would have us dealing with positives. So I'm going to multiply both sides of this by the following. By both sides here by this. That's going to give us a lot of cancellation on the right-hand side because I could break this up the following way. If we take this part that we already had on the right-hand side, because the exponents are negatives of each other for respective primes, then multiplying the things with the same prime base, we would have p sub t plus 1 raised to the 0 power on up through p sub s raised to the 0 power. These would be 1s. Product of 1s is still 1. So what we're left with you're left with this. On the right-hand side, P1 as one of the primes showing up in this prime factorization. Provides this product. By the way, that has nothing to do with Euclid's lemma. However, since this side equals this side, then p sub 1 would divide this. Now we could apply Euclid's extended lemma. That it divides one of these factors. And since we're talking about positive integers here and here, then applying Euclid's extended lemma again, then you have the prime p sub 1 dividing one of these primes along the way that we had on that side over there. Prime cannot divide some other prime. And also the way prime factorizations work, we would have gathered the highest power of a prime that would divide into something to express that as the prime factorization. So this is a contradiction. And what is that contradicting? That the differences were not all zero. This is showing that they are all zero. what good does that do us? Well, now we have these products of M and N here, here, everything that was along the way between 1 and S. And then we could say that we're undoing a proportion here. M over N is equal to F1 over E1 on up to M over N is equal to F sub S sub E sub S. Or put yet another way. All right, so we had that B was equal to this. We had all the same prime factors as in the prime factorization of A, and the question was whether the exponents could be different or not. Well, a little more rewriting here. From the index of 1 up to the index of S, we have each of those F's as being a multiple of the respective E times M over N. For lack of a better phrase, factor out the M over N. You look at this going backwards, we could, quote, distribute that power of M over N to each of the factors in that product and then multiply. So I've just reversed that. And this was the prime factorization of A. So we started off assuming that log of B in base A was rational. Shown that B must equal A to the power of M over N. M over N is some rational number. So this is a necessary condition for log of B base A to be rational. On the other hand, if B is a rational power of A, then by the definition of logarithms, we've got a base of A. The answer to the logarithm will be that exponent. By a process of elimination, we're talking about B here. So if we have that B is a rational power of A, then yes, the log of B base A will be rational. So now we also have a sufficient condition for log of b in base A to be rational. Therefore, this is an if and only if statement. And that's the end of the story for now.